The first topic that I want to talk about is the concept of a Lagrange multiplier. So the idea is that we want to simplify our life when we're talking about these boundary value problems, these maximization and minimization problems when we're on the boundary of a region or when we have some kind of a constraint. So the setup is we've got some function f of x that we want to find the maximum and minimum of. And we've got some level set, some set of points that satisfy an equation. And we want to find the maximum and minimum of this function, but on this level set. So for example, we might be constrained and we don't want to find the absolute maximum and minimum, or we want to be maybe finding the max and min of the function f of x on the boundary of something. And what Lagrange multipliers let us do is do this without finding a parameterization. We don't have to parameterize the level set. We instead use a method that secretly introduces an extra variable that we have to solve for instead. So here's the geometric idea behind it. So when we were looking at critical points, we used critical points those are the places where the gradient of our function is equal to 0. If the gradient of our function is not 0, then we can't be at a maximum or a minimum because we could move in the direction of the gradient and that would increase the function slightly, and we could move in the opposite direction and it would decrease it slightly. But if we're constrained, if we are stuck on the level set, g of x is equal to c somewhere, then we may not have all directions of movement available to us. We can only move parallel to the level set, which is the same as moving perpendicular to the gradient of the function g, because the gradient of g always points perpendicular to the level set. And so the setup is, if we're stuck, then the maximum or minimum of the function on this level set always occurs at a place where we have to move perpendicular to the gradient vector. And that's the same as saying that the gradient of g is parallel to the gradient of f. That's when we have local maxima and local minima on this level set. And using that method of finding when those two vectors are parallel is the method of Lagrange multipliers. So here's what we do. We say we want to find all those places where the gradient of g and the gradient of f are parallel on this level set. That means that one of them is a multiple of the other. So what we do is we solve that the gradient of f is some multiple of the gradient of g. And we introduce a constant lambda that we put in front of the gradient of g and use that to solve our system of equations. So here's an example of the type of problem where we might use the method of Lagrange multipliers. Let's say we want to find the maximum and minimum of this function, f of x, y, z is x plus y plus z on the sphere, x squared plus y squared plus z squared is equal to 1. Now, we could do this by parameterizing the sphere, but if we parameterize the sphere, then we kind of have to use spherical coordinates, and we get ourselves into a little bit of trig function hell if we do so. So what we do instead is we use a little method of Lagrange multipliers. We say, let's take the gradient of f. The gradient of our function f is pretty simple. It's just the vector 1, 1, 1 always. And we take the gradient of the function defining our level set. Our function defining our level set is x squared plus y squared plus z squared. So its gradient is 2x, 2y, z, z. We want those to be parallel. So we want 1, 1, 1 to be a multiple of 2x, 2y, 2z. And that breaks down into 3 separate equations. 1 is equal to lambda times 2x, 1 is equal to lambda times 2y, and 1 is equal to lambda times 2z. So 3 equations now in 4 unknowns, x, y, z, and this new variable lambda, but we've also got this constraint over here, x squared plus y squared plus z squared equals 1. And we solve that. Here's the 4 equations that we've written down, and we want to solve them. If we solve them, first, we can solve for x. X is 1 over 2 lambda. Similarly, y is 1 over 2 lambda, and z is 1 over 2 lambda. So that solves for all 3 of the variables x, y, and z in terms of lambda. But we haven't used the last equation yet, so we can plug in all those 3 points in, and we get 1 over 2 lambda squared plus 1 over 2 lambda squared plus 1 over 2 lambda squared equals 1. And we could simplify that by multiplying both sides by lambda squared and simplifying. It turns into lambda squared is equal to 3/4, or equivalently, lambda is plus or minus the square root of 3 over 2. If lambda is plus the square root of 3 over 2, we get this critical point. And if lambda is minus the square root of 2, we get that critical point. The value of our function was f of x, y, z, is x plus y plus z. So at this critical point, we take the value 1/3 plus 1 over root 3 plus 1 over root 3 plus 1 over root 3. That's 3 over root 3, or the square root of 3. Over here, the value is minus the square root of 3. And those are the global maxima and minima of this function on this particular level set, full stop. We don't have to do any trig parameterizations or anything like that. So for doing these types of boundary problems, the method of Lagrange multipliers is actually sometimes extremely helpful.